So as we get started on this, it's not an oversized crowd, so if you have any questions, I think we can probably work them in. I don't have a lot of slides, just basically some introduction to some areas. This is very demo intensive, so there's a number of things I want to cover. One, we're going to go ahead and, let's see if I can get the right one on here. We're going to go over some basics on using a logic analyzer. So that's always kind of cool. If I can get it hooked up properly when we get to that point. If we can't, then I got a video. I always have videos because you never know when shit's going to go to hell in a handbasket. So I've been working on this presentation on and off, and there's a few things that aren't 100% perfect. I apologize for that. It's kind of a work in progress and kind of work got in the way of some stuff. But we're going to get all the basics covered and give you guys some stuff that you can go out of here with and hopefully do some cool shit and break some hardware. And I know I got tons of broken hardware, so nothing wrong with destroying it. That's why they make garbage cans. So the presentation today is Uboot to root. So obviously we're going to cover some concepts around Uboot, some methods on some IoT to actually get into the Uboot console. And then we're going to cover a couple interesting things you can do. I have two different videos. Accessing Uboot's very similar. And then I'm going to do something outside of the Uboot also. It's something you often observe when you get a console on a bedded hardware, a consumer grade one, that often shows up. And I want to show that also. So hopefully this works out and we can get through all the demos without any major glitches. So let's start off with getting new batteries. Well, shit. It's the first one. So the first thing we're going to cover, what is Uboot? So Uboot is in the United States, Uboot is not a submarine. In Germany, Uboot is a submarine. Universal bootloader is what we're talking about, and it's used to load. It's loaded from flash memory, and it loads up, and it calls another storage area, or maybe the same storage area, and loads the operating system or kernel into memory and executes it and move from there. You can often access this via serial connections, so that's why we're going to use the logic analyzer to dig in to identify a serial connection. And then we get into, it has a very minimal command set. So you're going to see all the command set. You're going to see, looking at the environment, we're going to alter environment variables on the device. We're going to write them back to the device so we can get it to do certain things that we want to do. So why do you want to attack Uboot other than because you can freaking do it? Often you want to gain root access. Why do I want to gain root access? Typically there's two reasons for that. If I gain root access, I can actually monitor the running application, running code on the system. It gives me more insight in what's going on if we want to do further testing, looking for bugs, vulnerabilities, and things like that. It's also great for extracting firmware. If I want to get a firmware off a device, there's a number of ways to do it. I can pull the chip off the device. I may be able to use a reader on the device. Or if I can get root level access and there's exfiltration means either USB or network, we can go ahead and make calls right to often the block devices on the system and actually do DD copies off. And with DD copies, we can also alter that data, even if it's a non-writable file system, bring them back in. We're not going to do this, but bring them back in, unload the file system, rewrite the actual chip, the block device with DD, and alter the device, which is what we did last year. It was kind of the hard way. If anyone was in that presentation, we actually pulled an embedded multimedia controller, and we actually did that here, showing how to do that. So you can alter firmware. You can install your own preferred firmware if you want to alter the device and use it for some other purpose. I don't know why I keep using that, damn. So in the beginning, understanding and identifying. So if you're going to get into hardware, the first thing you want to do is start understanding hardware. And often one of the best ways to do that is literally tear the devices down. Let's start looking at them. So we have a number of them. This one happens to be a Luma. The Luma is a mesh device. It does Wi-Fi and Bluetooth. I use this example because it had a number of characteristics that I wanted to show and demo this evening. So we can easily look into that. So I always encourage people to go out and get your hands on hardware. Just buy any hardware. Go to a secondhand store. Buy junk off eBay. And before you start hooking stuff up to it and doing all this crazy stuff, just learn what's there. Open the device up and look at it. Let's get into identifying, is there a place where there's a header where it can potentially connect our tools into the system to identify what's going on there? Where are the memory chips? This happens to be a NAND flash chip. It's a SPI, serial peripheral interface type device. This over here is a controller for the Ethernet. This here, being an ARM IPQ4018, is a Wi-Fi chip. You can go out and pull down the data sheets on all these particular devices and look at them before you put power to it, before you do anything. Understand what's going on behind the scenes. Learn to identify that, because it's often very similar in nature as you start digging into these devices and their structure, the chipsets, the type of data, things you're looking at. So you want to be able to do that. Pop off these shields. The only thing you need these shields for is to meet FCC regulations, and we know where that's going. So pop all these shields off. Often I'll pop the shields off. I think this one actually has, let me pull this off here. This has a jumper wire on, just ignore that. I pass it around. So you can look into the device, and underneath here happens to be the RAM chips. And one of the easiest way to identify the RAM chips is you see all these squiggly lines. There's no straight shot lines going to the actual chip. They're all squiggly. The communication of the RAM chip is in parallel. It all has to get there at the same time. Thus, they actually function as delay functionality to be able to read and write to the RAM chip. So if you actually look at this underneath it, I'll pass it around, you can actually see all those squiggly lines. So it's a quick way to identify standard RAM chips on a device. So we're at a point where we're getting into basics. There's a number of tools that you can use to actually identify serial communications, which is a console you want to get on the device. And it's UART, Universal Asynchronous Receive Transmit. There's a number of tools of doing that. You can go out and buy a JTagulator, $160 or something like that. But this has other means too. You can use this for testing for JTAG. So what it does is you hook this up to all the pins, and it'll go through a series of sequences, and it'll send data to those and try to get a response back. And it'll do it with all the different pins at all the different baud rate speeds to try to identify which ones read, which ones write, and what the baud rate is. So it's somewhat convenient, and it works pretty good. You can also use a multimeter and actually measure voltage on it. And I've seen people talk about that. I actually think that sucks. Come on. There's a lot better ways of actually doing it. That is the cheapest way, for sure, but it's not a guarantee of what you're actually looking for. Another way is a logic analyzer. Now you can get these in different price ranges. This one here is like a $700 one. It's 8 channels, 100 megahertz sampling rate, so it's pretty high end. This one, unfortunately, they quit making. This was their 4. I don't remember what the sampling rate is. It's a 4 connector one. This used to be like $99, so it used to be cheap. I'm not sure, but Sele, when they quit producing this, told me they had a freaking shithouse pile of these things in the warehouse. Because I contacted them bitching about them because I wanted these for training purposes. So they sold me 6 of them for like $50. So that is an option to reach out and say, hey, do you still have that? I'm trying to learn and I'm looking to use your product. This is one of the better products, but there's a number of cheap ones out there that work pretty good. And I'd recommend this is the best way for doing analysis looking for UART connections. Also using the tool we're going to show, and I'll show some of the stuff in it. There's like 20 different decode protocols in the application that you can actually use. Everything from CAN bus, SPI, UART, the list goes on and on and on. And it comes in really handy for doing various other circuit analysis on the device. But it's great for figuring out what UART, if it's UART, and what the pinout is and what the baud rate is. Fairly quick with very little effort. So the first thing we want to do is do a demo. And let's see if this will actually work. Any questions while I'm fumbling around here?
Yeah, what is UART?
Universal Asynchronous Receive Transmit. It's a serial console. I'll use the expensive one because that's why I bought it.
Basically a single chip serial interface.
Serial when you're looking for serial interfaces, you can often find those on a lot of the MCUs or the processors. You also find UART used for inter-chip communications. Like if you have a Bluetooth chip on a board and you have a processor, whether it's a Wi-Fi processor or a standalone microcontroller, they actually communicate to each other over UART, and that seems to be the standard, and that's inter-chip communication. So you can look at that and decode that information there. But it's often on a lot of the microcontrollers and controllers, either by default or can be defined via GPIO, general purpose input output. And that's usually done programmatically on devices. And a lot of vendors will do that. They'll have consoles on most of the devices I open up have some form of console, especially if they have a full operating system of some type, some full embedded operating system. You're able to do that. Okay, let's come over here. And then it's all about time. We're going to get through this in time. We're not going to get through this in time. Okay. So on the 4-channel one, let's go ahead and wrong. And let me jump over here to this right here so you can see the device. So hopefully everyone can see that. Does it look good behind me? Can you see it? Okay, so maybe a little focus issues. I like this camera, but it has its own little issues. Okay, that's good enough. So everything's going to be backwards from what I'm looking at. So we can see right here is the actual pins. These are kind of high pins where we've actually soldered. The board will just have 4 holes in it. It'll be typically 2.54 millimeters. So you can buy strips of those. You can break off, stick them in, and solder them in to get the headers working. And then what we need to do is, I know that the first one on here, the very first one right here, is a ground pin. And the way we do that is we take a multimeter and we check it against, like in this case, these ground lugs that go to the ground plane on the device. We check to see does it ring out with a multimeter. So it's actually ground. So once you identify ground, you want to actually hook the ground ones to it. So in this case here, the lower wires on these rigs, all black on the bottom. Of course, they made the first line black too, which sucks. But the head on it's actually black. So that's a ground line. So if we can get my blindness to actually see this thing dark. And of course, watch old man fumble around here. And we got black, brown, black, brown, and red. We got 4 channels. We're going to look at 3 channels on this thing. I wouldn't really typically worry about the order. You can figure that out once you're seeing the communications. So, what we're looking for is serial, and I often check these. Not all of the headers that you find will have a UART on it. They could easily be a JTAG connection or some other in-circuit serial program connection. So we have that hooked up. So now what we want to do is jump over here to, I believe, this one. And it did detect it, my device, so we know that's good. And this program's called Logic, Sale's Logic. It probably needs updated. It's 1.2. But if we come over here, we can actually set things. So we can set the sampling rates and how long we want this to run. So we can go ahead and set this for 20 seconds. On mine, I can have up to 8 channels on this one. So once we get that set at 20 seconds, we get a power plug over here. And we're going to go ahead and start this. Once it's started, I'm going to put power to it. See if I had the power strip on. And apparently I don't have the power strip on. So let's turn it on. Okay, so now we got all the blueness on the back side of this and it's running. And we should capture some stuff here. So once it's done running, you can use the up and down arrow keys to look at this stuff. And we can see we have communication on channel 0. Usually when I see this and I only see one channel doing that and not like all 4 of them with similar communications on it, you usually quickly identify that this happens to be potentially UART. So what we can do is, and as I mentioned with the analyzers, you have a number of different analyzers. Let's see if we can show all the different analyzers. Let's see, get this up so you guys can see it. So we can see all the different analyzers that happen to be available. for decoding. So it's a fairly decent set. Sometimes you can actually pick up other decoders available as kind of plug-in type functionality. So come back down here. And what we're going to do is we are going to set up an async. Of course, I managed to lose my freaking glasses. Okay. And we know it's channel 1, so we're going to go ahead and set to channel 1. The next thing's the baud rate. So how do you determine the baud rate? There's a number of ways of doing it. One way is we can blow this thing out, and Logic gives you the ability to take a measurement. So you can take a measurement of the shortest pulse in there, take what that measurement is in microseconds, and divide it into 1. You're going to come up with a number that's going to be basically the baud rate, or close. It's not 100% accurate, it's close. You're going to land mostly at one of the standards. So you have a whole bunch of standards. So you can Google standard baud rates, and you're going to get a list of them running from 9,600 up to 200, I believe, or 200 and something. But IoT typically falls into 2 general areas 90% of the time or more, and that is 57,600, and the other one is 115,200. So I just pick, it's guess. It didn't work, change it. There's only so many options, and if none of those work, then you may have to dig a little, do a little math. If some vendor decided he wanted to get weird and play with your head by creating weird things. I had one device as an example. It actually changed a number of these other settings. So let's expand this out so you can see it. So you have 8 bits, 1 stop, no parity. I had one vendor that as the system booted up, you could see the whole boot process, and when it loaded kernel, it changed the parity bit. That took me freaking a whole day to figure out what the hell was going on. I'm like, this makes absolutely no sense. I know this is UART. I know what's going on. Why is this changing? And I'm getting gibberish all of a sudden. But I eventually got that figured out. So we're going to go ahead and set this to 115,200. And we're going to go ahead and save that out, and it should decode. So if we go ahead and we expand this out and we see that line up there, we can see that we've actually decoded this data. So we have these characters. If we come over to the right-hand side, we can see it all over here. So we can see it saying format, so format logic, and we can see that now we do have a true serial connection, and we've actually decoded it as UART, standard async communication. Any questions? I would recommend, if you're interested in hardware, get one. Either try to track down a used Sele. I love these, they're great devices. I do not own stock in the company, if you're not quite sure. The cheapest one right now is around 300, so it's a fairly heavy cost point or price point, but I think you could probably track down one of the smaller 4s, and you could always contact them and say, hey, I'm trying to learn this stuff, and I'm really entry level. They may sell you one at 90 bucks. They may actually go cheaper. I don't know if they happen to still have them. So I would not pass up that opportunity to give that a try. So the next thing we want to do is, now that we've done that, let's go ahead and disconnect that. And then what we're going to do is we're going to go over to a Shikra. A Shikra, we get here. So here's a Shikra. Shikra is a small device, and you can do a number of different things with this. You can do SPI, you can do some JTAG stuff, you use an open OCD. I don't use it for none of those because I'm lazy, so I buy the right tools. But this thing is actually great for UART communication. It's simple, it's easy, and there's a number of FTDI 232 devices. All different brands out there. Just pick one for this type of stuff. There's even a board that will actually have 4 of them built right into it. So then you want to go ahead and look at that. I don't know if I have a cable here. Make this a little longer. And I do. So we're going to go ahead and hook this up, plug it in here. So the things you need to be concerned with. As we looked at this and we connect it to this particular device, we also, we noticed where the ground was, so that's easy enough. Pin 18 is the ground, and then you have receive or transmit. The rule of thumb is, if this pin happens to be a transmit, okay, because we're receiving data from it. If it's a receive channel, you're not going to see nothing on it. It's going to be 0 voltage on it. So it's going to be on one side or the other. If both of those are 0, it's 50-50. Plug it in. If it doesn't work, plug it in the other side. And the goal is you have to go from transmit to receive and from receive to transmit. You know what I mean? So that they cross over or you won't get communication. Again, I usually don't give this much thought. I just plug it in. If it doesn't work, I swap the wires. Makes it fairly easy. So I'm going to power this off so I don't mess it up. And we're going to go ahead and hook. How are we on time? Running a little longer than I thought. But either way, we should get through this. If push comes to shove on presentations, I can run through some of the other videos. And this lighting is rough in here. Okay, I think I got it. And we're going to give it a whirl and see if I got it right. So I use, and you can use a number of different serial consoles. This particular one that I'm using is CoolTerm. I like CoolTerm. I just run it on my Mac. Comes in easy. So now we have to come over here to options. So we want to see if we actually see our device. If we do, there is the USB serial connection we have. We know what the baud rate is. It's 115200. The data bits were all the same. There's no parity, one stop bit. Only thing left was some terminal settings, so my terminal works right, handle this. And you can play around this, find out what works best from a terminal standpoint. You go OK, you connect to the device. I like that tick mark. That may mean I actually got it right the first time, but maybe not. So let's find out. I think maybe not. Okay. So let me swap these around here real quick. And of course, there's always a chance my thing is going bad. Oh gosh, come on over here, go in. That looks good. Oh, that ain't good. One of the things about shipping stuff and throwing it around in your bag is you like jam shit up. So we're going to start over, and I'm going to use another one that's kind of a little less mangled. Yeah, no, watching Deral plug things in is kind of boring. So just don't throw shit at my head. Okay, a little garbage there. Not sure why, but we'll find out. Now, this is another 50-50 whether I plugged it in right, because I wasn't paying attention. I'm hoping I got these things plugged in right. The wonders of live demos. Yeah, because if this part fails, then the next part can't be done. Of course, I forgot to do something like actually check to see if, oh gosh, yeah, cancel, let's disconnect, query, that's probably why it's not working. There we go, we got that, go OK, connect. Let's try one more time. Damn it. This doesn't work. I need to check my other connectors. Yeah, I'm having some problems here. Sorry about that, guys. Any questions why I fumble? Of course, I haven't given you anything to ask questions about yet, have I?
Have you tried the bus pirate serial adapter?
What's that?
Have you tried the bus pirate serial adapter?
I think the bus pirate's a piece of shit, but that's my opinion.
I've never used it, so I don't know.
Yeah, here we go. Okay. So we're booting up. It was just some connection issues. Hitting the key to auto boot. Okay, there we go. Okay. Of course, this device is messed up. So we have to, I apologize, apparently I grabbed the wrong device. Where's that device that's going around? Anyone still have that? Bring it here real quick. Yeah. Now, the reason why is one of these was used for another demo, so it wasn't reset properly. So the Bus Pirate has its traits, but and it probably worked pretty good on serial, to be honest with you. My experience with it was trying to use it to pull flash memory out, and it has a tendency to run a little slow. And it definitely, if you're in a VM environment, it has serious problems with the USB bus on timing issues. I actually took the one that I had and reprogrammed it as an SDK 500 to do connections to at mega chips to be able to pull the firmware off those. And that it worked really good at. Oh, you gotta be shitting me. Why is this thing playing with me? I apologize, damn it. This is crazy. Should have just rewrote the other one. Could have done that. Okay, let me go ahead. So it's already booting up. So you can get the whole idea of the boot. Okay, so we get a log on this thing. I apologize for that. That's kind of screwed up on my part. I had them all plugged together, plugged into use, and then of course they got unplugged in the bag, being bounced around into one. The pins were all mangled, and there's actually a couple shorted out to each other, so that's why I pulled that out there so it wouldn't be any more problems. And this thing will come up as a Luma. We don't know the password. I've got the hash off of it. We weren't able to crack that, which is not uncommon for a number of these devices. So one of the things we want to do, and let me jump over now that we're at this point, let's go ahead while that's running up. Let's go ahead and step over here, breaking in console, methods for gaining access. So there's a number of different methods, but you want to be able to get into Uboot. Uboot has what's known as a boot delay. So you can fire up a device and you can actually see it count down from 3, 2, 1. That means it has a boot delay in place. Most of the boards you're going to run into, that's going to be set to 0. That means you're not going to be able to halt it and go into Uboot mode. And it can be set in seconds, but you have to get into Uboot console to be able to set that. So we want to be able to do that. So the way we're going to actually do that is an attack we know and refer to as a pin glitch, for no better terms. And the way that works is we have a memory chip. In this case, this is much easier to do on this way. There's 2 memory chips. There's one on the underside of the board, happens to be an 8-pin SOIC SPI flash chip that actually holds Uboot. The chip on the upper side happens to be a NAND SPI chip. This one, this is a WSON socket. It's like 6x7 or 5x6 millimeters, pretty small. And that's the actual pin out. So the ultimate goal is, as Uboot loads up, what you want to do is prevent it from, after it's loaded, you don't want to do anything while it's loading. Just load it. You want to actually stop it from actually being able to read the kernel. By default, Uboot will fail into a console when you actually do that. And here we have the actual pin outs. So the pin you want to take the ground happens to be the slave out for the SPI. This is the outgoing data. Now, as I show this to you, don't go out and go, hey, let's just start shorting shit out and see what happens. Because you will find out quickly what will happen. And it won't go good for you a number of times. This attack works a lot of times. Doesn't work all the times. I was doing an engagement for a customer. We had a similar layout like this, but they were reading everything from the one chip. It's a big timing issue there because it's just literally milliseconds. So you have to try like 40, 50 times before you get it to fail into Uboot console. All I managed to do is have it to fail in by wiping out the Uboot. somehow. It was kind of weird. So in the demo, what we're going to do is we're actually going to ground this out as the device is booting up. And as presentation has been going so far, this is liable to go to hell in a handbasket too. But I hope not. I usually put a lot of time into working through these demos so that we can have good demos, live demos, and make sense. So we have this device. So we're actually going to power this device off, and then we're going to go ahead. I don't want that. Document camera. We don't want that. We actually want the USB microscope. Okay, so we get into the microscope here, this USB microscope, and we kind of bring this thing down, bring it in focus a little bit. Here happens to be the actual chip. So I've already hooked to the ground plane, this wire here, to the ground plane. And the goal is as soon as you power this thing up, you want to be able to ground out pin 2, which happens to be this pin right here, okay? And while you're doing that, you don't want to short out other shit, because that's not good. So we're going to try to do this. And we got to be able to watch the console on the other side. So let's shorten this up a little bit. Let's bring this over. So we can see some kind of traffic taking place over here. Let's clear this data. Hopefully we'll get this the first time. I was doing it the other day, and for some reason, like, this is really easy. It took me like 4 times. I'm like, well, you're not even in front of people, Daryl. You're not supposed to screw this up when you're in your lab by yourself. Yep. Nope. Too quick. Power it off. Boom. So now there's a number of different commands. There is print environment, print env, and we can see the, can everyone see that good? I tried to make it big enough so you could. So we're actually able to see the environment variables. So we can walk up through here, and there's a couple interesting environment variables. Right here we have, let's see if this laser pointer works. Damn, this thing's like shit. Oh, that's why I didn't have it turned on. What a dumbass. So I'm a real comedian today. So if we come over here, we have boot delay. So we have boot delay right here. So we can actually set that. So the first thing we're going to do is we're going to set boot delay to a number, and then we're going to power it off and back on again, and you can see how we can actually halt it. So let's go ahead and do that first and see if we can get through that without blowing my leg off. And the way we do that is we want to do set env, boot delay, and we're going to set it at 5. We put that out there. Let's go ahead and scroll our print environment, see if that'll actually look right. So we have boot delay set to 5, and then what we want to do is we want to save the environment variables out there. So now we've written the entire environment variables back to the system. Things that are weird. This should normally work. You should be able to write back to the chip, no problem. I did actually encounter a piece of hardware. We were actually at this level here. I was changing environment variables, and I said save env, and it literally wiped the entire flash chip blank. I've yet to figure out why. The saving grace was, and this was a gig for a customer, the saving grace was, and they had no idea why I did it either. I actually made a copy of the firmware by pulling the chip off and pulling the firmware and putting the chip back on. So all I did was pull the chip off, reflash the firmware. I typically pull chips if it's like an SPI, because if you're actually going to read and write to an SPI chip to pull flash memory, you have to actually take the main processor, reset, and you have to take the CPU into reset mode, or it'll interfere with that communication. I typically notice if it's an I2C chip, I2C is a bus protocol, so if you hook up to that, you will actually put a request on the bus to communicate with it, and typically you could do those in circuit. Just a couple quick notes there. So from here, there's a command. Let's look at the commands real quick. So $1 here, or question mark, you can actually see the commands. Uboot will be compiled different for every product with different functions. So you can see a massive amount of different functionality that may be there or not be there. I've seen the command structure to be really minimal, and I've seen it be very intense. So here's the command instructions, and you can do all kinds of things. You can read from memory, you can boot from TFTP, which we're actually going to do to get some level of access to the device. So once we've saved that out, one of the commands is reset, which actually calls the CPU to go reset mode, and it should reboot for us, and it should come up at one point and actually prompt us so we no longer have the glitch. So then you just hit the enter key, and there we've broken out of it because we put that delay function in there. So at this point, some of the things we want to do is, the ultimate goal is to actually get root access to the actual device. So at this point, with the delay put in, only with that delay set other than 0, the function called boot command will actually work, okay? So at this point, you can actually put specific boot commands in there. In our case, I am actually going to just cut and paste to be able to do that because I don't want to type all this stuff. And we're not going to write it in there. What we're going to do is we're going to run it from the console, run it from the Uboot console. So what we're going to do here, based on the system booting up, we know where everything is in memory typically. I have to check one more thing before we run this. It's going to go to hell on us. A couple things to mention. We have, this device actually has server IP. This happens to be the IP address of the TFTP server. So before we get started, let's go ahead and cancel out of that. Let me check real quick here. We have a VM running here. And I'm just going to go ahead and, what was that? It was 182. So we need to set it to 11.182. Wrong. 11.82. So I'm going to go ahead and just do this under edit connections. Or connection. Change this to manual. Add 192.168.11.182. Did I type that in right? Okay, and then 255.255.0. Okay, and then we want to tab out of there. And then we want to go ahead and save that out. And then we have Ethernet connected up in my wiring mess. And we're going to plug the Ethernet into this. Luckily, this thing had a couple Ethernet ports. Yeah, I wasn't sure how long these videos would take, or these demos would take, so we're still making good time. We won't be able to go through all of them, but I can run a quick video and talk you through some of the other stuff. So at this point, let's see if we can actually ping it. Ping 192.168.11.182 using Ethernet. And of course, it's not there. Okay. Damn. With the split screen, my screen got even smaller, so I'm like going blind here. To enable network. Okay, now it's up and live. So at this point, we can actually do TFTP. It's going to take the TFTP variables that are actually in this particular Uboot, which is the actual server. It's going to go out, and what I did was I went out, since this is an IPQ 4018 chip, There was some OpenWRT projects out there for it. So we're actually able to compile one. We didn't get all the pieces working. One of the reasons is that secondary chip on here happens to be a very non-standard chip. So I ran out of time. The process would be to actually rebuild the kernel with a new device tree where I define all the variables for that particular chip into a .dts file, which was, we just walked through that process recently, so I didn't get it actually into the system yet. So we're going to go ahead and run this, and if it works out, it's starting to load. So at this point, it's actually loading over TFTP server. Oh, damn it. But it does give us a level of access. So the next phase of it would be get to recompile for the right DTS for the right device tree. That would give us more access to other pieces of the actual device. And there, we're actually got root level access to the device. So we're able to actually see some of the stuff. So, oh gosh, everything's not working now. Oh, don't tell me this thing's decided to fuck with me. It's not disconnected, it's there. Scan tree, playback. Okay, scan tree, document tree. Damn it. Shit go hell in a handbasket quick, doesn't it? But you see we came up with root level access. From there, you can go ahead and go into proc and request a dump of the MTDs and identify all of the actual partitions that are actually lined out on the actual chips. Any questions? We're going to go over something else here in a minute. Hopefully it goes good too. Any questions? Any concerns? Any beer bottles to throw at my head? Yeah.
So just real quick, so the TFTP boot option, is that usually set to nothing?
It's usually set to nothing. What it's going to do in this case, it's going to pull from boot IPQ, which is going to pull from the flash memory. It's defined in Uboot in this particular case. There's a number of different ways you can actually to break into this. Some of the other examples is in the Uboot arguments, the environment area called boot args. In boot args, you can often, at the end of the line, there's a couple things you do. It doesn't work on this one, but it works on some of them. You can actually put a 1 in there, which tells booted in single user mode. You can actually put single in there, it varies, or you can put emergency, and that'll often give it to boot into that. One of the other things I was going to show before I managed to disable myself somehow. There we go. So just disconnect it, reconnect it. Here, let me show this cat slash proc MTD. And we can actually see partitions on the initial chip. There's a secondary chip that contains some other file system data that would be where we often want to get in this case. But it's about how the chipsets are lined out, what's available, and actually building those DTS files to actually put that into the device tree, which would be one of the next steps. So one of the things I want to do now is just to show this to you. There's other functions that often show up when you're in these consoles. So let's go ahead and go. Yeah, my serial port's acting up. Connect. Reboot. So we're going to go ahead and we're going to let this come back up. I think I keep bumping these wires. Oh, I know exactly why it's doing it. This thing was actually shorting out over here. So we're going to let this come up, and what we're looking for is an F switch show up. Got to be quick. Or not be quick. I missed it. I must have missed it. There we go. That F switch, let's see if we can scroll up so you can actually see that. I see this a lot, and there's a lot of cool stuff you can do from here, because this F switch will actually put the device in single user mode if they compiled it to actually be able to do that. The difference is now that we're in here, if we try to read any, we can actually do and see the actual devices under proc MTD, and you can see the few that we actually missed down toward the bottom that are on that other chip set. So we're able to get into this, but now we're in this single user mode, and literally none of the drivers, none of the functions, none of the pieces are actually in place to actually communicate over Ethernet or communicate over USB. I actually tried to enable the Wi-Fi on this thing, and it literally just kicked my ass. Nothing would work. So Wi-Fi, Ethernet, neither one of those was I able to actually communicate with or get fully functioning. So then I circled around to the USB. See, this thing come up and it says USB, and it says all this data here, but you still can't address the USB. There's no device in the system. Even though it recognized I plugged something in, there's no device. So one of the methods that I have is I found out that you have to actually build the device from scratch. So we're actually able to, oh shit, that sucked. That didn't work. Come on over here, control. Get it right. Wrong. There we go. So you use make node, and generally the way the make node works is we have to define some variables. With make node, we set, this is just a Linux read, write, read, write, read, write. We have to define the device and where we want to put it. And this B switch lets us define two things, which is the major and minor. The major, in this particular case, that number replies to an SD device, one of the block devices that you can actually configure into a system. The one, from what I understand, is actually the sequence of device. If I had multiples on there, they would be numbered differently as I'm setting them up. So it'd be 8.1, 8.2, 8.3, and it would be SDA, SDB, SDC, whatever the case may be, and you have to set the minor to be appropriate to actually communicate that. So we're going to go ahead and we're going to put that in there. One of the next ones we had to do was I checked the device. Let's make sure we can actually see it. I like to put that in there. Don't do that. So we actually do run a check on the device, and it comes up, and I don't actually see any errors on it, which is kind of cool. The ultimate goal in this case here is I want to get the firmware off, and I want to get it off other than pulling it from a flash. Pull it from a flash, I get a blob. It's all the pieces, all the parts. Trying to separate it out is very difficult. At this point, I have all the mounted partitions. I can DD all of them off and get the individual partition structure. So the next thing we want to do, and I always do this, is format the device. So we're actually going to format SDA. So this will take a second. So any questions? No, because they could come from literally anywhere. It's kind of amazing. A lot of them come obviously from China. The sources in China are like kind of iffy. So you usually have to screen through a whole bunch of sales crap a lot of times to drill down into it. Some of the bigger manufacturers have better resources to actually go to the sites for those particular chips. You know, Texas Instruments and things like that are much easier to track it down. You still run into a lot of cases where you're dealing with OEM devices, and you know you have to sell your firstborn child to actually get your hands on them. Yes, sir.
You mentioned that some devices, the timing is so difficult when they boot up, you might have to try 40 or 50 times. Do you think it'd be worth it building something with just a couple of relays to go ahead and push the power on and wait so many cycles and then switch and then ground out?
Yeah, I guess if you could determine that timing cycle, you know, I mean, you can it's still very random because you don't know where it's going to be. But is there a way to identify that? Yeah, that would be an interesting project. I'd love to be able to do that, and maybe hook it up to something where it just restarts the system and keeps going until it figures out what that is. But again, as an example, you never know with power off, on, off, on, off, on, off, on, what will happen. I've seen some strange things happen where the device just says, screw you, and doesn't come up anymore. We had one we were using for training and ended up getting cycled. The Uboot environment variables went away. Okay, so that came up. So at this point, one of the things we can do is we want to go ahead and mount the device. So we have to make a directory. So now we're on a device and all of the directory structure is only read-only. So the one way around that is all these devices boot up and put a lot of stuff in temp. Temp will be read-writable on these embedded tech. So we're actually able to create that there. The next option is let's go ahead and, hold on a second. We're going to go ahead and we're going to mount it. So we're going to mount the USB. Yeah, it mounted okay. It goes through, says, I don't know what this is. Says, oh yeah, I know what this is, and it mounts it up. The next thing we want to do is, now that we've done that, let's start grabbing crap off this thing. And since we knew the partitions, let me see, is it 12, 10? Let's look at these partitions again. So cat/proc/mtd. So we see these partitions here, running out of time. But the interesting thing, when you're dealing with embedded systems, you're actually going to have two UBI root systems or two root systems. These are typically the main root file system structure you're actually going to see. The reason why you have two of these and two kernels is upgrade. That's how you do upgrades on the system. If you look into Uboot, there'll be an environment variable that tells what structure to actually use on that boot up. So what happens is when the system does an update, it receives the update. What it'll do is do DD to the one that's offline, because they can unmount them DD right to those. And then what it'll do is it'll change the environment variable switch as part of this. It'll boot back up. So if the whole firmware update fails back to the valid structure. And that's why they do that. Versus, you know, how many times power cycle in your house happens to do an upgrade, what's going on. You'd be killing devices all over the place if it wasn't for that. So next thing we want to do is we're going to go ahead and DD partition MTD10 over to the device. And this process here works pretty good, and now we can get it off. Now we have the actual file system partition. Running out of time, so I'm not going to show it, but what you would do is you could easily take that, now that I have it, and actually do unsquash it. So you can do bin walk. You don't even need to do bin walk on it because it's just going to be a squash file system. So you just basically unsquash it out, and now you got it blown out into a writable format. You can go in and create your own usernames, passwords, everything all into this file system, and then go back and make squash, and then take that image and DD it right back onto the device, right into that location. Make sure the environment variable is set to point to that particular one, and you boot it up. Or you can be risky like I did last year when I did the demo. When I initially did that, when we were talking about the embedded multimedia controller, I just wrote the image to both of them. It's either going to work or it's going in the trash. So it's kind of still running here. So one of the things I wanted to show, and I'm going to be around tomorrow if anyone wants to see it or actually do one of these attacks. I have some Hue devices, or had some Hue devices. Oh, here we are. These is what we used at RSA Sandbox Village, and also we use these at the DEF CON IoT Village for hands-on training, which we're going to be back this year doing some stuff. But you can do that glitching on here. The cool thing with this, the manufacturer actually put the root password hash as an environment variable. So yeah, you connect into there and you just delete it. You know, you do set environment security and 2 tick marks. It wipes it out. You write it back to the system. You reboot it, and you root. Game over. It's a really funny example. I was hoping to show that. So as you see, we kind of finished up here. We're able to actually write that out to the actual USB now that we built the environment all the environment for it. And now we can pull off all the partitions on that disk and do analysis, and it's much easier than trying to explode it out from an actual blob dump or a flash dump. And I got 1 minute, and then they're going to drag me out of here. So any questions real quick? So we got through all the demos. Yes?
Say like a flash dump, you don't get like that, I guess, partition or like structure. Like you can't like mount it as like a device or something.
Yeah, you can mount this up if you wanted to.
Like flash ROM.
No, yeah. When you pull the flash ROM off, I've never been able to mount that up straight up. Not in that environment. I've never been successful in doing it. I've gone through and I've tried to do that. I have actually taken them off. I've taken the objects off that way and was successful in one case to actually DD the whole flash onto it. This was kind of weird. The whole flash, it wasn't an SPI, but the whole flash block onto a USB and got it to mount up when I plugged it in and booted and mounted it up. And it actually mounted up as a file system on another device I had. But no, I hadn't been successful in that. So that kind of finishes everything up. I hope you enjoyed it. We got through all the demos except for the hue, in spite of the blind old man glitches. So I hope you enjoyed that. I'm going to be here through tomorrow. Please talk to me. If you have any questions, catch me or reach out to me online. I'm always online. So thank you very much.